Hello, my name is Richard Fan. This is Lab 2 Charge Tapes Revisited. For the introduction, the purpose of this lab was to use the fundamental physics principles of Coulomb's law, Newton's second law, and distribution of charges to use data collected from a previous experiment to calculate the electric force on charged pieces of tapes. Materials used a clear tape, ruler, flat surface, and blocks to hold the tape up. The system was taped in gravity from Earth, and the environment was air. Computer models used to grow script, and a sneak peek of the results is that the Coulomb's law, Newton's second law, and distribution of charges was used to calculate the new magnitude of the charge based on line charges, which was significantly greater than the charge associated or calculated assuming point charges. For the fundamental physics principles, Coulomb's law is the amount of force between charged particles at rest, and the formula is that it's equal to the k constant times the charges of both the different particles divided by their distance separation squared. And this was used in with tandem of the Newton's second law, which states that systems change in momentum proportion to the net force acts upon the system, to use the force being equal to 0 so that we could equate the gravity and the mass times gravity equal to the Coulomb's law. And then the charge distribution is how the charges are arranged within an object can cause different electric fields. So I'll briefly go over this. Basically, in the experiment, you use the tape to be read from another piece of tape to charge it, and then using a combination of negative charge, then find out if it attracts or repels. And since it attracted, we knew it was positive. The system was a tape and hand. The surroundings was air. This one we use two charged pieces of tapes and get them to repel, and then we measure the separation distance, and then we use that to then calculate the charges. And the system was states and gravity, and the environment was here. These are the variables I used within my code. Length was 0.25 meters, mass was 0.25 grams. The OG charge for my thing was 1.38 e⁻⁸ coulombs. Distance to is 0.026 meters. So the coding questions, this will be answered later on. So this was my variables that I used within my code. The mass, the length were all from previous thing, and the distance to 0.026 is here, and n was just a random number I chose for the amount of charges. We don't actually know how much our particles were in the line, and this is the Q that I eventually got from using process of elimination and just trial and error to get the forces to equate to each other. This is the E field that I just got from lab 1, put it into lab 2. And these for loops ran throughout each of the particles in the line charge to get the force with the new charge. And then these are just the errors to get the model to look correct. So these are model, and as you see here, each one of the particles or charges in the line charge each contribute a different arrow, and this then equates to the electric force and gravitational force. As you can see here, this is a typo. They're almost the same. It's off by like 0.00001, and the original charge is 1.385 e⁻⁸, and the charge that I got from the coding was 3.1532 e⁻⁸. So what are the assumptions? So one of the assumptions were wrong, but the assumptions that were true was we did ignore air resistance on a moving object, and we did assume that each U-tape you made about the same amount of charge, and it was evenly distributed along the length of the tape. So we did not treat this as a point charge because, as the skeleton code provided, it created a charge for even distributed distance that created into a line charge instead of point charge. And potential errors within our code or within our lab is that due to assumptions, the calculation is not going to be exact to the actual real world model. Inaccuracies with measuring, because we couldn't mishandle the tape, we were scared of the charge getting messed up based if the different materials were touching the tape. We couldn't actually get a very accurate measuring because the ruler wasn't placed on the tape, and that's other factors like humidity from the surrounding could affect the transfer of charges. And what if you had a model that each of your tape has a single part charge like in the previous lab and compare these estimated models? So basically the line charge model had 2.278 times more charge than the point charge model. And why do these estimates differ? Which value is more likely to be closer to real value? Why? So basically the estimates differ because when looking at a point charge, all the charges concentrated at the same point with the same distance. However, when line charges are used, some of the charge results in a stronger electric field as it's closer, while others are weaker, needing more charge to create the same force. And as you can see here, it's because all of these charges exerts an electric field on each other, but some of these are higher distance than others, which creates a stronger field or weaker field. And our line charge model is more likely to be closer to real value because in real which the tapes have a distribution of charges throughout the length of the tape and are not concentrated at one point. And that is my lab. Thank you.